we have two more topics to discuss in this with regards to recombination and generation, and the first is something to do with the capture cross section. So, this is not a new concept that is going to change things that we have learned, but it is a different way of viewing the RG capture, and it is a very geometrical method of viewing the capture of electrons in RG centers. And the argument for this goes like this. So, let us say you have a volume in a semiconductor. Okay. So, we are looking at the actual physical picture in a semiconductor, and this volume has got a cross section A, and an electron is sort of travelling through this cross section, it is going through this. Okay. So, let me draw that better. So, the electron is actually travelling through that, and let us say the electron has got a thermal velocity Vth, and Vth is what? It is kT by 2 because it is just one dimension here, and mv square by 2. So, that is a relation that is dictating what is Vth. It has got some thermal velocity, and therefore, in time t the electron would have travelled a distance of Vth by t. So, let us look at this volume, which has got an area of cross section. It is a cuboid which has got an area of cross section A, and it has got a thickness, or the depth is Vth into t. So, the volume of this cuboid is Vth into t into A, and inside this region of space you have some Rg centers. So, these are all Rg centers that can capture electrons, and these centers have got a capture radius. So, if an electron were to move inside here, it is definitely captured, it is trapped, and if it does not, if it can escape all these centers, then the electron is not trapped. Okay. Therefore, since these centers for capture have to be empty states. Okay. So, we have the Rg states, some of them are filled, some of them are empty, and it is only these states that can capture electrons. Okay. So, the number of capture sites, okay, inside this volume is Pt, which is the number of capture sites per unit volume into the total volume under consideration. So, the total volume under consideration is Vth into t into A, and the volume occupied by the capture sites is Vth into t into A into Pt. Pt is a number per unit volume. Now, let us project this entire 3D structure onto a 2D plane. So, we sort of squeeze in and we flatten out all the Rg centers. So, you have the Rg centers here, there might have been two say behind one another, and these are all regions occupied by the Rg centers, and this entire area has got an area of A, and the total area, the total projected area as seen through all these Rg centers is the number of Rg centers to some extent into the cross section area of each Rg center. Okay. So, we will define this cross section area. This is the area within which if an electron were to enter, the electron were to be captured. We will define this cross section area as sigma. This is the number of Rg centers, and if these Rg centers are seen independently, that is there is no intersection between them, the projected area of all the Rg centers is essentially this. Okay. And this sigma can sort of take an effective value. So, if there is a lot of intersection between these Rg centers as we project them. So, let us say it is a very nice geometrical concept. So, let us say there were two Rg centers just one behind the other, and they appear like this in this projection. So, sigma could take an effective value. Okay, it need not, it can be defined a little differently. So, essentially what we are talking about here is that this area represents the shaded region, which are all the capture zones, and A is the total area, and an electron is going to go through this region and is going to go through at a random point. So, what is the probability that the electron is captured? It is the probability that the electron lands on one of these shaded regions, which is Vth t into A Pt sigma by A, which is this term here. What is the rate, the probability rate that the electron is captured? It is the time derivative of that, which is simply this term. Now, the probability rate times the number of electrons per unit volume is essentially a measure of dN by dt. Okay. So, dN by dt then becomes Vth into Pt into sigma into n, which according to our old definition was Cn n into Pt. So, if you remember many slides back, we said that the rate at which electrons are captured. So, this is only capture. So, we are not saying dN by dt, this is only capture of electrons, the rate at which they are captured, okay, or trapped. We had said that that was proportional to n into Pt, and we gave a proportionality constant called Cn for the electron capture. So, we are talking about the same derivative here. Therefore, these two terms are the same, which implies that we get a geometrical insight into what Cn is. So, you see n and Pt can be cancelled, and therefore, your Cn is nothing but the thermal velocity into sigma. So, it is the same concept, but it is a very geometrical way of viewing the same idea. Now, the final topic that we will study under recombination and generation. Okay, so, this is a typo, there is no thermal there, I am sorry, quite a few typos in this topic, but please do bear with me. The final topic that we will study in recombination generation is to do with the concept of quasi-Fermi levels. Okay. Now, this is a concept that we will not be using quite a bit. We will not really use quasi-Fermi levels through the course. We will manage it without using this concept, but it is a concept that you need to be aware of. Okay, and I think it is best discussed with an example. So, let us say you have an n type semiconductor in equilibrium. Okay, so, Nd is 1e15, that is its n type semiconductor, therefore, the donor concentration is 1e15 per cc, and we are asked to locate Ef minus Ei. So, we had an intrinsic semiconductor that was Ei, the intrinsic Fermi level, and after doping it n type, the Fermi level moved closer to the conduction band, and we want to calculate what this is. Now, there are two methods to calculate it, because I know that n is equal to Ni e to the power Ef minus Ei by kT, and P is equal to Ni e to the power minus Ef minus Ei by kT. Therefore, if I use this approach, my Ef minus Ei is equal to kT ln n by Ni, and if I use this approach, my Ef minus Ei is equal to minus kT ln P by Ni. So, let us see what both these approaches give you. Now, Ni, let us say, is about 1e10, which means my n, since it is doped and since the dopant concentration is much larger than 1e10, we will say n is approximately 1e15 per cc, and P according to the mass action law is all at equilibrium. So, therefore, according to the mass action law, it is Ni square by n, which is 1e5. So, if we were to plug in n by Ni, so n by Ni is 1e15 by 1e5, 1e10, which is 1e5. And what is Ni by, what is P by Ni? P by Ni is 1e5 by 1e10, which is minus, I am sorry, 1e minus 5. So, you plug in these two values here, you will find that both these options give you the same answer, and you will find that Ef minus Ei is approximately 0.29 electron volts. Now, let us take this semiconductor out of equilibrium. Okay, so let us say we throw some light on the semiconductor and we generate 1e12 electron pairs, electron hole pairs. So what has happened to the carrier count now? Now n was initially 1e15 at equilibrium, we have now added 1e12 carriers, and therefore 1e15 plus 1e12 is approximately 1e15 because the amount of injected carriers is about 1000 times less than the equilibrium carrier concentration. On the other hand, P was only 1e5 per cc in equilibrium, and now you have added 1e12. So therefore we have made a significant change in the count for P. So P has now become 1e12 per cc. So although n remained the same, P has suddenly changed. Now let us try to calculate EF minus EI. We will use both these approaches. Now clearly you can see that there is going to be a problem because the EF minus EI calculation, EF minus EI calculation using the electron count has not changed because n is still 1e15, but the EF minus EI calculation using holes has to change significantly because the hole has now gone from 1e5 to 1e12. So this used to be 1e5 per cc, but now because of light being thrown on it, it has become 1e12, and you will end up with a very different answer. You will end up with 0.17 electron volt. So which of these is correct? Okay, so there seems to be a paradox here. So therefore when we discuss non-equilibrium conditions, okay, we cannot allow a common Fermi level for electrons and holes, it cannot be the same. Therefore the electrons now take a Fermi level called EFn, which is the quasi Fermi level for electrons, and holes take a Fermi level called EFp, which is the Fermi level for holes, and therefore we must rewrite these equations. We cannot use one common EF, therefore EFn minus EI is 0.29 electron volts, which means the quasi Fermi level for electrons is still very much the same as the Fermi level at equilibrium, but the quasi Fermi level for holes has shifted from the equilibrium Fermi level value. Okay, it is now only 1.17 electron volts above your EI or yeah. Okay, so this is the idea of quasi Fermi levels, and this is something that we will not use. We will not be using this concept, but although it is useful to know, it can be a very powerful tool while performing calculations, but we will try to avoid it. Okay. So with this we come to the end of the study on recombination and generation, and we now have the tools to understand how dN by dt is affected by recombination generation mechanisms. Okay. And we will now embark upon establishing a concept or an idea which is called as the continuity equation, or a complete budget of the carrier counts in the volume, which was the big picture we have been discussing, and we will use that to study semiconductors in various conditions. So we now consider mechanisms of charge transport. Okay, so far if we take a summary of everything we have done, we have established a method to count the number of carriers in the conduction band and the number of holes in the valence band. So we can count them, and in order to count them we established what the density of states was, we established what the Fermi function was, and with these two we could evaluate the values of n and p. Then in the generation recombination processes we saw how the count, the dynamics of the electrons in the conduction band and the holes in the valence band is influenced by the various features. So now we are trying to establish the concepts of charge transport. So these are the mechanisms by which the electron and hole concentrations could vary, okay. And now based on these variations or based on these counts of electrons and hole concentration, we want to establish what the currents would be in a semiconductor and the different mechanisms of charge transport in a semiconductor. So, we are gradually heading towards something called as the continuity equation, which is a very useful concept and a useful idea in order to solve out the reaction of the semiconductor for various situations. So, let us focus on two most important methods of charge transport. Okay. So, we have already come across one phenomena which was called as tunneling. Okay. So, we will skip that for now. We are not interested in tunneling in this particular discussion. We are interested in two particular modes of charge transport, and they are called as drift and diffusion. Okay. So, drift and diffusion, and in a very little while I will explain to you what these two terms imply. Okay. Now, of course, there are other methods of charge transport, and I think the most prominent one is tunneling, okay, which was you have the wave function of the electron on one side of a barrier, and the wave function does exist on the other side simply because there is a non-zero probability that the wave function can get past this barrier despite the energy of the electron or the energy of the carrier being less than the barrier height. We have already looked at this in our brief discussion in quantum mechanics, and we will use the concept of tunneling later on, but it is not the focus of this particular study. So, first let us look at the drift current. Okay. Now, what does drift current mean? Drift current simply means that your electrons and holes are moving through the semiconductor because of the presence of an electric field. So, you have a semiconductor, you have your let us say you have your conduction band, you have your valence band, okay, and you have free electrons in the basically the electrons in the conduction band, and you have holes in the valence band. And the moment you apply an electric field, what would happen is these bands would actually bend, okay, as shown here, and all the electrons would run downhill and the holes would run uphill. Okay. So, that is the way the energy band diagrams are drawn to define the lower side, if you might allow, as having the higher potential. So, all the electrons would run towards the higher potential side, and all the holes will run towards the lower potential side. So, this is the response of the electrons and holes to an applied electric field. So, essentially what this requires is you need to have free electrons in the conduction band, and there are empty states, and these electrons sort of move through these states, whereas the electrons in the valence band move through these vacancies, okay, which essentially gives you this picture of the holes moving towards the other side. Okay. So, that is what is happening when you apply an electric field through across a semiconductor. So, in order to get a quantitative estimate as to what the drift current is, if you think of the semiconductor, okay, so you have applied an electric field. Let us say the area of cross section is A, and let us say the semiconductor has got a length capital L, and let us say we have applied a voltage, okay, VA across this. Okay. Now, as long as the electric field, okay, which we will sort of write down as VA by L. Okay. So, it may not be perfectly correct, but for all practical purposes for the time being we will just say it is VA by L. It is a very uniform electric field, there is nothing else inside, and you have a field of VA by L. So, the electric field in the semiconductor allows the electrons and holes to move to the opposite electrodes. Now, the electron flux, okay, so if you look at the current density, and we will say that the drift current density has got this what is a subscript dr, okay, as is written here. The drift current density, the total drift current density is the drift current due to electrons and the drift current due to holes. Now, do these two currents sum or take a difference? Okay. So, if you apply an electric field, the holes which are positively charged run in the opposite direction as that of the electrons, and therefore, these two currents sum up to give you the total drift current. Now, what is the drift current due to electrons? It is the total charge, okay, per unit volume. So, we are talking the drift current density. So, this is the current per unit area, okay. So, we are talking about I by A. So, this is nothing but the total charge of free electrons per unit volume. So, N is the number of electrons per unit volume that is in the conduction band, so which is the free electron concentration. Q is the electronic charge, and therefore, Qn is the total charge of the electrons that are responding to the applied field into the drift velocity of the electrons. So, this gives you a measure of the distance covered by the electrons per unit time, and therefore, these two terms together is nothing but the rate of change of charge per unit area, which is nothing but dq by dt, where which is all taken as a per unit area estimate. Okay. So, that is the drift current due to electrons. Okay. So, you have q and vdn, and similarly for holes you have qp vdp, where vdp is the drift current due to the applied electric field. Now, we have already looked at the concept of mobility of carriers, okay, and we did notice that in the presence of a low electric field. So, you have the electric field and you have the drift velocity of the carriers. At low electric fields, the drift velocity is linearly proportional to the electric field, and then it sort of saturated out in some of the semiconductors. So, at low electric fields, the relation between the drift velocity and the applied electric field is given by Vd is proportional to the electric field, with the constant of proportionality being the mobility of the semiconductor. So, therefore, we can rewrite the drift velocity of the electrons and holes as Qn mu times the electric field, or mu n times the electric field, where mu n is the mobility of the electrons, and Qp mu p into electric field, where mu p is the mobility of the holes. So, the summation of these two terms gives you the total current or the total current density due to drift, okay. And this is a very useful relation to keep in mind, wherein the electrons and holes contribute to the current together. So, certain points to note here. So, the first thing is you might wonder what happened to the electron charge being negative, okay. So, well, that is already taken into account because the electrons and holes are moving in the opposite direction. So, if you are going to look at the conventional current, okay, so we are talking about the current in the opposite direction of the electrons. So, the electron flux is one way, the current is always the opposite side. That is the way current is defined, okay. It is from the positively charged electrode to the negatively charged electrode, and therefore, the current is in the same direction as that of the holes. And since the electrons have got negative charge and are moving in the opposite direction, it is equivalent to having a current of plus q n mu n electric field in the opposite direction of the current, okay. So, this is the relation between the drift current density of electrons and the drift current density of holes, and the summation being the total drift current. Now, this essentially leads to the formulation of Ohm's law, okay. So, for example, let us look at the total current, okay. So, we have the total current through the semiconductor being J times the area, okay, and we already know that the drift current density, okay. So, we are only interested in the current due to the applied current due to the applied voltage, and the drift current density is nothing but q n mu n plus p mu p into the electric field into the area gives you the total current. Now the electric field is nothing but your dV by dx. Okay. You can throw in a negative sign, but we are interested in the magnitude of the current, because in the case of, in order to derive Ohm's law, I really want to establish a relation between the voltage, the current and the resistance of a resistor, and therefore the direction of the current is not really a matter of concern right now. Okay. So therefore we will not worry about the electric field being minus dV by dx, we will just say dV by dx and instead use the modulus of the current. Okay. So if so this happens to be the current through the device. Now if you just solve this differential equation, so as so instead of VA by L, which is a very liberal way of defining electric field, we have defined the electric field more carefully as dV by dx. Okay. So V by L is a very liberal way of defining the electric field, particularly when a semiconductor is involved, as you will soon see. Okay. So that's probably true for an insulator, but not so true for a semiconductor. So let us define the current versus voltage in this particular manner. So if you solve this differential equation and you integrate the current with respect to dx, and as you go from one end of the semiconductor to the other, so let us say you go from 0 to L, the voltage varies from 0 to VA, and by just solving this differential equation you find that your VA is nothing but 1 by q n mu n plus q p mu p into L by A into I. Okay. So this is the relation between the applied voltage and the current through the device. So what does this remind us of? So this term here is the resistance. Right. So firstly it tells us that the current voltage have a linear relation. So the voltage is equal to I into R, and this R has got a term which is equivalent to the resistivity. So this particular term is the resistivity, where R is rho L by A. L and A define the geometrical parameters, and most importantly rho is the resistivity, that is 1 by q n mu n plus p mu p. So the resistivity of a material is taken to be a constant, okay, but now we know what that constant depends upon. It depends upon the mobility of electrons and the mobility of holes, and the total electron concentration per unit volume and the hole concentration that is the number of holes per unit volume. So in a metal you do not have holes, and therefore the resistivity is simply 1 by q n mu n. Alright, so that is drift current. So it is a response of the carriers to the applied electric field which is obtained by applying a voltage across the device.